And we are back. Okay, so sorry about that little interruption. My Surface decided to freeze on us. So let's see if we can pick up where we left off. Okay. So last time we ended up using logarithmic differentiation, I believe, and we actually solved this all the way, and then the computer froze, so I'll continue from that next problem moving forward. Okay, welcome back to you too, Shay. So find the equation of a tangent line to the curve x squared plus 6xy plus 9y squared equals 25 at the point 2,1. This tends to give people some trouble, so I'll try and help out with using some implicit differentiation. So what do we need to do? Well, we need to take the derivative with respect to x on both sides. Oh, by the way, you can check and see, always double check to make sure this point lies on the curve. This way, when we use the derivative, we're going to be able to plug in. If not, you need to use some tricks and algebraic techniques to try and find that point on the curve. So keep that in mind. So we have the derivative with respect to x of x squared plus 6xy plus 9y squared equals the derivative with respect to x of 25. And so one of these is really easy. Hopefully the right hand side you can see right away is going to be equal to 0. We'll come back and touch on that. So everything we're doing is derivative with respect to the variable x. So notice you have an x here. That'll be an easier one. So the derivative of x squared, that should be 2x. Now the next piece though, plus 6xy, that has an x and a y, right? So the y's are the tricky cases. So what we need to do in this case, since we have a product of two functions, we'll have 6 times d dx of x times y, and I gotta be a little careful, I'll put it all in parentheses here, plus x times our derivative with respect to x of y. Okay? And then we need, last but certainly not least, we can pull our 9 out in front, and then we have a dx of y squared. And all this junk should equal 0, right? Because our derivative of 25 is equal to 0. Okay. So, answering the question about the technique in the last problem, yes, you can use logarithmic differentiation. So, sorry, moving back to this problem, since we see this product or quotient rule, can we always use logarithmic differentiation for any product or any quotient? The answer is yes. And in terms of what happens in general, if it's only 2 or 3 terms though, so if you have a product of 2 or a product of 3, at the end of the day what happened was we finished with, if you look back at the old video, you have 1 over, I believe it's r of x times r prime of x. Right? So the way to solve for this, you're going to multiply this on the other side of the equal sign. So you'd actually have more simplifying to do in a lot of cases to plug back in if it's only 2 or 3 symbols. But when it's quite a few like this, this will be logarithmic differentiation will cut down on your time drastically. So sorry to get sidetracked there, but I want to answer any questions from before we got cut off the last time. Alright, so we want to find the equation of a tangent line to the curve x squared plus 6xy plus 9y squared equals 25 at the point 2,1. And you can check and see that 2,1 is on the curve. And you can do that by plugging in 2 for the x. So you get 4 plus 12 times 1 is 12. So 4 plus 12 is 16. Plus 9 times 1, so that's 9. So 16 plus 9 is 25. So they match. It is on the curve. So that's why we can go through and actually get this and plug it in after we find our derivative here in a little bit. So what do we have? Well, we have 2x plus 6 times these derivatives. So 6 times, now the fun part, derivative of x, well that's just 1, so we're just left with 1 times y, which is y, plus x times, the derivative of y is 1, but this is essentially, with this y here, we have to use the chain rule. So we get the derivative of y as 1, but we need to multiply by the derivative of y with respect to x. And that's what implicit differentiation essentially is just a chain rule over and over again. So the only thing when you have y's, you multiply by this dy dx at the end. So the next piece, 9 times derivative of y squared. Well, we use the power rule for that, so you get 2y, but remember we have to use the chain rule, so essentially you have this times dy dx is what we're multiplying by there, and we get equals 0. Okay, so when we take a look to what's going forward from here, we would need to solve for our dy dx. And how do you solve for a variable? And notice there's no dy dx squareds. If you do ever see that, that's actually differential equations type stuff. You solve for when you square derivative and things of that nature and solve for it. But in this case, what do? Well, we try and isolate the dy dx on one side and everything that doesn't have a dy dx on the other. That's pretty much how you solve for any variable. So before we do that, let's make our lives a little bit simpler. We get 2x plus, let's distribute that 6, so you get 6y plus 6x dy dx plus 18y dy dx equals 0. Okay. Now, moving forward from here, where do we go? Well, we get we want to move all these terms that don't have a dy dx in them over to the other side, so we just subtract them both. And notice we have dy dx, and we can factor it out of these two remaining terms. You have a factor here, you have a factor there, so you factor it out. Dy dx in times the quantity 6x plus 18y, right, equals negative 2x minus 6y. Okay, so moving forward from here, let me write that on up here. What do we do to solve for dy dx? Well, we just divide by what's multiplied by dy dx. So you get dy dx equals negative 2x minus 6y all over 6x plus 18y. Okay. Yeah, we could simplify, we could factor out a 2 from both the numerator and denominator, but that's really not the necessary point here. What we're trying to do is find the derivative with respect to x at the point 2 comma 1. So we just plug that in. So we get negative 2. Our x value is 2, so we have a 2 here. Minus 6 times 1. And then 6 times 2 plus 18 times 1. We can simplify this just a little bit here. So what do we have? Negative 4 minus 6 makes negative 10. And then what do we get? 12 plus 18, that looks like 30. So that's just negative 1/3. And now we're ready for, we want the equation of a tangent line. What does this represent? Well, this represents whenever you have dy dx at that point, this is a slope of the tangent line at 2, 1. Okay? So what we do? Well, we go use our point slope formula. It goes y minus y1. What's our y1? Well, it's going to be just that 1 right there. So y minus 1 equals negative 1/3 times the quantity x minus our x1 is just going to be 2. And if you need to solve for y or something like that, you just add 1 over to the other side. It's that simple. And if you need to distribute, do what you got to do. But at the end of the day, that's basically all we need is a formula of this type unless something specific is asked. Okay? If there's any questions, just let me know on that one, and we'll move forward. So that's the end of the derivatives. Now we're moving into the application of derivatives. So for those of you at the Armstrong class, you don't need to check this out, but this is coming soon to a class near you. For those of you sticking around for E-Core stuff, yeah, we're going to get the whole kit and caboodle here. So we have a plane flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when it is 2 miles away from the station. So hopefully you'll love, we'll have some beautiful drawings going on here. So I'll draw my radar station. So we'll have and some little radar going up here. So we have a plane, and we'll draw this out. We know the altitude was 1 mile, right? And that's constant. But this plane, and let's see, it's like Picasso. It's a beautiful drawing of a plane right there. Don't let your eyes fool you. So what we have is some plane right here, and things that are changing, right? We have this x here, the distance from the plane to the radar station in this direction, and then we also have this L sitting here. And we know that this is a right angle because it passed directly above. So we have a triangle. In fact, we have a right triangle, and so maybe we can set up some sort of like ratio for the right triangle that might help us solve this. So let's think about some of the things we'll have in time. Notice the speed, right, of the airplane is 500 miles per hour when it passes directly over. So this, what that represents, speed is miles per hour. So you have x as a distance, and so we'll use dx and then dt to represent that 500 miles per hour. It's the speed of the plane. And so we'll need that somewhere along the way. Now, sooner or later, we're going to try and plug in after we do some work, because it's talking increasing when it is 2 miles away from the station. The distance away is 2 miles. So we'll need to work with that when the time comes. But the equation that we can set up relating the x, the L, and the 1, well, you just have x squared plus 1 squared equals, and that's a 1, don't let your eyes fool you, equals L squared. And the reason I didn't use d for distance, just from the standpoint of d is going to be our derivative in time. So now this is a related rate. What do? Well, we take a derivative with respect to the variable t. So you take d dt of x squared plus 1 squared equals d dt. Feels like it's a wrestling move or something, a DDT there. So what do we have? Well, when we take the derivative, the 1 squared, that's a constant, so that isn't going to make a difference. So at the end of the day, we have 2x. Remember, we have to use our chain rule, so derivative of x with respect to t, so you get dx dt. All right, equals, well, this will be 2L times dl dt. Okay, and what are we looking? Find the rate. So rate is talking about something with respect to time, rate at which the distance from the plane to the station is increasing. So we want to solve for dl dt. So at the end of the day, I'll put it over to this side. dl dt equals 2x divided by 2L times dx dt, which is the same thing as just x over L times dx dt. Okay, how do we solve this now? Well, we need x and L. So what we know is at some point, this L equals 2 miles. Now you might say, ruh-roh, we don't know what x is, but actually we can figure it out, right? If you look, you have from this formula, I'll draw this over here. Sorry, I ran out of room a little bit. So you get 1 squared plus x squared equals 2 squared. And you might have already recognized what triangle this is. So notice we get x squared equals 4 minus 1. So x equals, usually you'd say plus or minus 3. Square root of 3, I'm sorry. But we're just going to say positive square root of 3, and the reason why is we're talking distance, and this is miles. So x equals square root of 3 miles. You can't have a negative square root of 3 miles. So that's what we're looking at there. And so now we're ready to kind of finish this problem. So what does this equal? This equals the square root of 3 over 2 times dx dt. We already had that. That's 500 miles per hour. So we have 500. And if you take 500 and divide by 2, notice you get, if you want to simplify this, this is 250 times the square root of 3, and it's a rate, so this should be miles since we were talking miles, and we were going per hour on that, so miles per hour on this. Okay, so 250 times square root of 3. And if you need a nicer answer, you can just plug that into a calculator if you have one. If not, just leave it like that and you're good to go. So the next problem, in terms of applications of derivatives, now let's take a look. And once again, feel free to ask any questions up in that chat if you have them. So find the point on the line y equals 2x plus 3 that is closest to the origin. Ooh, so what happens? Well, you have, first off, what's the origin? Well, origin is at point 0, 0. You go 1, 2, 3. You're going to have 2x plus 3. Let's see, let's do negative 2. So negative 2 would correspond to the point negative 1. And so you have some little line. I'm not saying this is the perfect line, but you're finding some point on this line that's going to be closest to that origin. Okay, there's actually a nice rule you can use and actually have your answer right away. But in terms of what we have, let's say you have some point xy, right? And then you want to go distance. So let's call this, instead of distance, we'll call this L. So what we have is L equals the square root of, well, it goes x minus 0 squared plus y minus 0 squared. And we're trying to optimize this thing. So when we do an optimization, there's actually a few different approaches, but you want to get your equation, unlike the related rates, you want to try and get this down to one single variable. And you might look and say, okay, this seems impossible. We got an x and a y. But notice we have y equals 2x plus 3, and that's what's coming to our rescue. L equals the square root of, this becomes x squared plus, instead of y squared, because we can just drop the zeros, by the way, folks, that you get 2x plus 3 now, squared. So with this in mind, what actually happens at this point, well, we're trying to solve. You actually have a couple different approaches, by the way. You could do, you could square both sides, get rid of the square root, and then use kind of an implicit differentiation to solve that. That's actually the easier approach. I'll show the harder approach just so people can be somewhat familiar. And what do we have? We get L prime equals, remember square roots become 1 over 2 times that square root, right? So the square root of the inside, x squared plus 2x plus 3, the quantity squared, but times the derivative of x squared plus 2x plus 3, the quantity squared. Okay, so what does L prime equal? I'll write that over here. L prime equals, you can take this derivative, since it's multiplied by our fraction, just move it up top. So the derivative of x squared is 2x. The derivative of 2x plus 3, the quantity squared, we're going to need to use a chain rule. Bring that 2 on down out front. So you get 2 times 2x plus 3 raised to the first power. But times the derivative of the inside. The derivative of the inside is just derivative of 2x because the derivative of 3 is 0. So derivative of 2x is just 2. Okay? And all of this is over 2 times the square root of x squared plus 2x plus 3, the quantity squared. And usually you have to check for all these critical points and things of that nature. In this case, you don't really have to. And the reason why, because the denominator, well, you do have to, but in terms of the denominator, I should say, the denominator can't equal 0 because you have 0 here would mean that you're getting positive 3 here, and you're squaring every number. So you're always getting some positive format down below. So we don't have to worry about that piece. So what that means is we can just take the 2's, and now you got to do that to each term. We cancel off this 2 and we cancel off that 2. And what are we left with? Well, when we're looking at this, we want to set the whole derivative equal to 0 because that's what optimization does, right? So 0 equals, we have x plus 2 times 2x plus 3. Okay? And so the reason why we're setting this equal to 0, when you're talking closest to the origin, you want to minimize, I should have said this at the first get-go, minimize distance. And that's all we're doing, is we're minimizing distance. Okay? So 0 equals x plus 2 times the quantity 2x plus 3. What does this become? Well, this is, so you get 4x plus 6 right here. And so we'll get negative 6 equals 5x. And so x equals negative 6 over 5. Okay, and we had that y equals 2x plus 3, which we'll check in a second. But first, what we have to do is x equals negative 6/5. So we have our number line, right? And we got to determine if this happens to be, so this is your x value, and then we get 0 for L prime up here. And we got to look at numbers to the left of negative 6/5 and numbers to the right. Well, the easiest number to the right is to plug in 0. So we'll start with that. Plug in 0, you get 0 here. You'll get 3 times 2, which is a positive. And then, as we mentioned before, the whole denominator is positive, so we don't really have to worry about that. So just the numerator. And so now, instead of the negative 6/5, let's take negative 10, because that's easy to work with. Negative 10 makes negative 20 here. And in the numerator, with this 2x plus 3, this negative 20 plus 3 is negative 17, so that's negative there. Negative plus a negative makes a negative up top, and we said the denominator is always positive, so negative divided by a positive is negative. So what is the graph doing? Well, it's decreasing, and then it's increasing is what the graph is doing. That's what that tells us right there. So we have information about the graph. We know it's decreasing to increasing. What actually happens then? Well, that means we have a minimum. So winner, winner, chicken dinner right there. There's our minimum x value. Right? And since there were no other critical points, that's the only one we have to check. So since that's the minimum, all we need to do is find the y value. So our y value is, well, we get 2 times negative 6/5 plus 3. So what is that? That's going to be negative 12/5 plus 15 over 5. So I believe that's 3 over 5, correct? Correct me if I'm wrong. So our coordinates is negative 6/5, or our 3/5 is closest to the origin. Okay, hopefully that made sense on that one. Let's take a look at our next problem, where we're heading now. Ooh, it's integration time. My favorite time. So, integrals. This pops up quite a bit in Calc 2. You're going to need to know this inside out, up and down, for those of you who haven't taken that class. So, let's get started with integrals. One thing that we do know is we're starting off with an easy one. So, the derivative of, just an FY, cosecant x equals negative cosecant x cotangent x. Now notice, we can reverse this process, and I'm not talking about the bounds just yet. We'll get to that in a second. If we take the integral of cosecant x cotangent x in dx, what does that equal? Well, notice if we were to take this derivative of cosecant of x, that puts a negative out front. So how do we take care of that negative and make it turn into a positive? Because that's what we're reversing this process. So what we need to do is multiply this derivative times a negative 1. That'll make this negative times negative and a positive. So what happens is the antiderivative of cosecant x cotangent x is just negative cosecant of x, and then plus some constant c usually. Okay, so what do we have in mind here? Well, this thing equals, we know the antiderivative, and you might say, okay, we need to plug in a plus c, but actually we don't. When you have bounds, if I put a plus c in for pi over 6 and another plus c in for when we plugged in pi over 2, what happens is the c's cancel. So when you have a definite integral, that's what this is called when you have bounds, a definite integral, we don't have to worry about the plus c part. Okay, just worry about the main component of that antiderivative without the constant. So what this becomes is negative cosecant of pi over 2 minus a negative cotangent, or not, minus a negative cosecant, my apologies, of pi over 6. Now there's one assumption I'm making here that I needed to be careful on. Is this actually continuous, right, on that interval? So the main problem here is from pi over 6 to pi over 2. Is this defined at pi over 2? So just an FYI, right, just so you can all see it, you have your x value equals cosine of theta, and your y value is equal to sine of theta, where your thetas are 0, pi over 2, and this is pi, this is 3 pi over 2, and you can keep on going around the circle. So at pi over 2, well, what are the coordinates at that point? It's 0 and 1, right? And so notice the y value at pi over 2 is 1. So by the way, sine of pi over 2 equals 1. And so we don't have a problem because cosecant is 1 over sine and cotangent is cosine over sine. So we have 1 in the denominators both times. So it is defined on that interval. That's something I should check all the time. I got a little bit lax there. Just you do the problems enough, you'll recognize whether or not it's defined on that interval. But just kind of keep that in mind. So now, where do we go from here? Well, we got to figure out our solution. So negative cosecant of pi over 2. Remember, that is negative 1 over sine of pi over 2. And minus, once again, if you don't like the cosecant, you can do the cosecant here. Minus and minus, by the way, makes a plus. Plus 1 over sine of pi over 6. Okay, how do we finish this problem now? Well, pi over 6, that's a triangle that we know. And if you have pi over 6 here, that means you have pi over 3 here. That's a 30, 60, 90 degree triangle. And so what that means, that's a 1 square root of 3 and 2. We just kind of talked about it in another problem. So you have the 1 go here, the square root of 3 goes here, and the 2 goes on the hypotenuse. So in terms of the pi over 2, we have sine of pi over 2 equals 1. So we have this is negative 1 over 1 plus 1 over sine of pi over 6. I'll write it as a fraction on top of a fraction for now, but then we'll fix that in a second. So opposite, which is 1, over the hypotenuse, which is 2. And so notice when you flip that and multiply by its reciprocal, you get 2. So this is negative 1 plus 2, which equals exactly the number we were thinking about, I'm sure, 1. Okay, so we have our solution to that problem then. Moving forward to the next one. We have an acceleration function in meters per second given by this a of t equals 2t plus 3, and you have an initial velocity given by v of 0 equals negative 4. Can we find the velocity at time t? So how do we figure this out? Well, the key on these problems, first off, if you have v prime of t, that equals a of t. And so what does that mean? That's your relationship there. That means the integral of a of t dt should equal the velocity plus some constant c. And that's the moral of the story here. So when it comes down to it, what we have is if we calculate this a of t dt, we should know it equals v of t plus c. So essentially our v of t plus c should equal the integral of the a of t, which the integral of a of t would be just the integral of 2t plus 3 dt. Okay, so now moving forward from here, we want to solve for v of t. Right, what's our c value essentially? So in this case, I'll erase the plus c. Essentially, we have v of t equals whatever the constant's going to be right here. So how do we do this? Well, you take this to be 2. You can pull that constant out in front. And for those of you that don't remember, it's 1 plus 1 over 1 plus 1. And then plus 3t, and then plus a c. So notice this makes 2 up here, and this makes 2 down below, so this 2 and this 2 can cancel. So we're left with v of t equals t squared plus 3t plus that constant c that we talked about before, v of t plus c, right? So we need to get this information in play so we can figure out the full velocity function. Notice we have -4 equaling v of 0. But v of 0, that means you're just plugging in 0 squared, 0 for all the t's, plus 3 times 0 plus c. So what does that mean happens? Well, we have at the end of the day, you get c equals -4. Okay, so now we can go back to this equation. I'll start real quick and plug in c equals -4. So we have our velocity equation equals t squared plus 3t minus 4. And that is that. Okay. Hopefully that makes sense on that problem. If not, ask questions. That's what I'm here for. So let's move on to the next one. Evaluate the integral e to the x times the square root of 1 plus e to the x dx. So with this one, this is a little bit nastier than the other two. We're going to have to use what's called a u substitution. This is a little bit too nasty for us to integrate as is. So in order to do that, there's a few different ways people use u substitution. So we have e to the x, square root of 1 plus e to the x. What I always tell people is, what makes this hard? Most people will say the square root, and I say, if it was just a square root of x, would it be hard without the e to the x and all that stuff? And most people say no. You could use the basically reverse power rule there, versus the power rule to try and get that antiderivative. So the real problem is this 1 plus e to the x and the underneath the root. And so that's what we'll do. We'll let u equal 1 plus e to the x. Now, if you make a wrong guess and things don't cancel out, does that mean, oh, we're done and we should just give up? No. Just make another guess, and that's fine. Over time, you practice these enough, you start to get the hang of what your u is and what your du is. Okay, so our du in this case, what would that be? Well, it's going to be e to the x times dx. Now, the reason why you don't see anything happening with the 1, the derivative of 1 is 0. Okay. So now, there's a few different ways. People try and catch this the way it's written. What I often teach my classes to do is dx equals, notice, and I just switched the sides. So you have a du, you have to divide by e to the x on both sides. So when you rewrite this integral, you can rewrite it. You have an e to the x. Notice we have now a square root of u. Okay, but dx is du over e to the x. So let's see. And if we've done this correctly, we should have everything with an x involved cancel out. And that's exactly what happens. You have this e to the x and this e to the x cancel out. And so now you have square root of u du. Now some of you might know this one off the top of your head. What I'd recommend though, if you don't, just write it as u to the 1/2 du. So when you take the antiderivative of this, it's the same thing. Got to just use that power rule for antiderivatives essentially. You get 1/2 plus 1 up in the exponent over 1/2 plus 1. And if you take 1/2 plus 1, oh, and we forgot one big part here. This is plus c. So this is u to the 3/2 over, put it in parentheses, 3/2 plus c. And sooner or later, you'll actually get in the habit of being able to, rather than divide by 3/2, you multiply both sides, multiply by the reciprocal of that, so you get 2/3 u to the 3/2 plus c. Now, we can brush that up a little bit because, first off, we didn't start with u. We want to put in what our u is. But notice that u is equal to 1 plus e to the x. So this is 2/3, 1 plus e to the x raised to the 3/2 plus c. And that might be a fine final answer. Sometimes you need it simplified in a certain format. So what does that mean? You get a 2/3 1 plus e to the x. Well, what we'll do is rather than write a parentheses there, that 1/2 power associated with it is the square root. And then you have that cube up top. That means you cubed this whole thing. And plus c. So you might see it in that format as well. Or a 1 plus e to the x in parentheses cubed, and then take the square root of that whole thing. All of them are the same answer, just a slightly different format. Okay, hopefully that helps with that problem right there. Let's take a look at our next piece and see what happens. So the next problem coming up. Ooh, so we have an integral from 0 to 1 of e to the x plus x, or e to the x plus 1 in the numerator and e to the x plus x in the denominator, and then we're taking our antiderivative with respect to x. So in this case, when we're actually working with these problems, what do we have to do? Well, we have to basically find our u again. And what makes this difficult? Most people will say the fraction in the denominator involved with the fraction. So we'll start this off. We have e to the x plus 1 over e to the x plus x dx. And you can see if it works on the first try. If not, as I said, try and try again until you get one that matches. So notice we get e to the x plus x. So that means du equals derivative of e to the x is e to the x. Derivative of x is just 1. And so we'll take that and then we'll put a dx. Don't forget the dx at the end. So you get dx equals, and I'll write it on this side this time, du over e to the x plus 1. There is one caveat here. When you have a definite integral, rather than waiting and putting back in terms of x and plugging back in, you can change the bounds. That way we don't have to, once we solve in terms of the antiderivative in terms of u, we're done. So that's what we're going to do. And the way we'll do that here, we'll plug in u of 1 for the top bound. So u of 1 equals e to the 1 plus 1, right? And which is just e plus 1. And u of 0 is e to the 0 plus 0, which equals just 1. So your new bounds become, if we've done this correctly and things cancel out, get 1, the integral from 1 to e plus 1. Okay, so we shifted our bounds. The denominator is now u. We still have an e to the x plus 1 up top, but instead of dx we have du over e to the x plus 1. So what happens is the e to the x plus 1's canceled just how we wanted to. We don't want any x's and u's at the same time. So this whole integral equals the integral from 1 to e plus 1 of du over u, or 1 over u times du, whichever you prefer. What is this antiderivative? Well, if you look up your list of antiderivatives, you will have that this is actually just natural log of u, and then usually plus c, but since we've evaluated and we're evaluating at points, we put 1 and e plus 1 as our bounds for our definite integral. So notice our answer is just natural log of e plus 1. And since that's a positive number, I don't need absolute value technically. Minus natural log of 1. And you might recognize that natural log of 1 is 0. So our final answer is just natural log of, and I'll drop the absolute value as I said since that's a positive number. So natural log of e plus 1. That's our final answer for that one. Okay, I think we got one or two more here. Evaluate the integral from 0 to pi over 2 of cosine of x, sine of x. What makes this one difficult? Well, some people will call this a product. Technically, this is a composition of functions. So what we need to do when we're solving this one, we have an integral from 0 to pi over 2 of cosine of x, and then a sine of x dx. If we just had this be sine of x, like this whole quantity inside was just x, we'd be done. So that's the problem point. So we'll say u equals sine of x. So du equals cosine of x dx. So dx equals du over cosine of x. Okay. So now we need to plug in and change our bounds. So we need u of pi over 2, by the way. And we just talked about that. The sine of pi over 2. Just a nice trig function. You can look at your unit circle and see that that's 1. And then we need u of 0. And we can find out that sine of 0 is just 0. So this becomes the integral from 0 to 1. This is cosine of x. This is sine of u. And dx is du over cosine of x. So it seems like a problem at first, but then we see our cosines of x's cancel. And what we're left with is the integral from 0 to 1 of sine of u du. So that's not a bad integral, and we won't even have to plug back in with the bounds here. So if we have this, we take the antiderivative of sine. That's going to be negative cosine of u, evaluated at 0, 1. So this is equal to negative cosine of 1, which whatever number that is, and then minus minus cosine of 0. Cosine of 0 is actually 1, so this becomes negative cosine of 1. Minus a minus makes a plus, and we said cosine of 0 is 1. So you can call this negative cosine of 1 plus 1, or just 1 minus cosine of 1. All does the same thing at the end of the day. So let's see if there's the last page. Don't have anything. I'll toss in one more just for a bonus. Evaluate the integral let's do, okay, I'll give you a tough one. So let's say e to the x over the square root of 1 minus e to the 2x. So usually we'd say the square root is what causes the problem in the denominator, so we let it be 1 minus e to the 2x. But when you do a u and a du, you'll find u equals e to the 2x, negative e to the 2x, or negative 2e to the 2x, or u equals 1 minus e to the 2x, and then du equals negative 2e to the 2x. And that doesn't match the numerator. So that one doesn't work. So the trick, what I tell people, in order to see this one's not as common. And so with it being a challenge problem, it's kind of fun. Check out what happens. Notice you have an e to the x to the quantity squared. And what you can do is you go u equals e to the x, and du equals e to the x dx. So if that's the case, dx equals du over e to the x. So this thing can be rewritten as e to the x, oh, I forgot my dx there. Dx there. E to the x over square root of 1 minus u squared. You might say that might not be doing us any help, but actually it does. It does us a ton of help, and I'll explain why in just a second. So this is one of those where e to the x's cancel, and you get this thing is just 1 over the square root of 1 minus u squared du. You may recognize this antiderivative, or you may not. It just depends on how much practice you have. This is the arc sine. So it's the arc sine of u plus the constant c. So this one finishes off with arc sine of e to the x plus a constant c. So hopefully that helped all of you with the problems. If you have any other questions, feel free to post them in discussions, or just let me know what questions you have, and I'm happy to help as much as possible. So wish you all the best luck with the upcoming exam, and as I said, let me know if you have any other questions.